And I know that there's a few new faces to introduce around, so maybe we could just do like a quick round of introductions, if that works. Fernando, I'll maybe ask you to go last, so hopefully by that time Dom will show up and then you don't have to do it twice, but either way you might have to. I think everybody knows Doug and myself, so maybe we can start with John.
Hey, yeah. So I'm John Kadaif. I work with DS Geophysical out of, we got offices in Vancouver, Toronto, and in Saskatoon. That's where our base is. Get lots of land for pretty cheap there, so we can keep all our development there, instrument-wise. I also brew beer, as Doug said. I try to supply with the SimPEG group when I can. Yeah, I'm mostly looking on DC problem, IV, and then now airborne, or I guess audio AMT, airborne AMT. I don't know what everybody wants to call it yet, but I know some people have reserve about calling it airborne AMT. It's actually not that, they say. So, but yeah, things along those lines.
Soggy.
Hi, I'm Soggy. So I'm mostly working on airborne electromagnetics, particularly in the Central Valley of California, for mapping out the hydrogeological structure and helping local counties to build up their geological conceptual models and manage their water, like a groundwater management. So that's the main thing. So it's not like there's no direct linkage from MT and there, but I'm still interested in the numerical aspect of parallelization, how are we going to really optimize and run things in the cloud. So that's why I'm here.
Sorry. Joe. Or are you?
My name's Joe Capriati. I'm currently a postdoc under Doug with basically developing on SimPEG efficiency kind of targeted code, like targeted code development for certain projects and stuff. I did my doctorate at Colorado School of Mines under Yagwo Lee. And currently, my doctorate was in, my thesis was on coupled flow inversion, coupled fluid flow inversion of time-lapse gravity data. So I just got started here up in UBC, and then I got stuck down in the States with my wife.
Where are you right now geographically?
I am in Colorado, in Denver, just outside of Denver.
Devin.
Hi, I'm Devin Cowan, and I work for Doug at UBC. And I think my part of the SimPEG project for MT is focusing a lot on tutorials and documentation. I've been doing a lot of natural source stuff in the past maybe year and a half with the UBC GIF codes and working with our sponsors. So I've had a lot of interest lately in kind of developing workflows and really seeing what the practical needs are for people who start with a data set and would ultimately like to invert it. So that's kind of my involvement with this.
Go for it, Fernando.
So hi for the new faces. My name is Fernando Perez. I'm faculty at UC Berkeley. My training, I actually did my PhD in Colorado, not at Mines, but at Cedar Boulder in the physics department. And I was trained as a particle physicist. I've had a weird, long, winding path that has mostly involved a lot of software. I've been kind of very involved with the scientific Python ecosystem from the start. IPython was my kind of PhD procrastination project that grew into Jupyter, so that's going to become a big job. And today I'm faculty in stats, and my interests for the context of probably this discussion are really that I've explicitly chosen to kind of focus the domain aspect of my research around the geosciences. I probably should have done a geophysics PhD instead of a particle physics PhD if I had called things right. And so that's actually how I connected with Lindsay a couple of years ago, and how she came to work at Berkeley was an explicit attempt at basically focusing on the intersection between basically physics as represented in problems in the geosciences and geophysics, and questions in data science, statistical learning, machine learning, without losing sight of my interest in open source and open science and the development of open source tools for scientific research. And so last year we were awarded a grant from the NSF for a project that we titled Jupiter Meets the Earth, that Lindsay played a huge role in developing that proposal. And that's kind of what brings me to this meeting, that the framing of that project, and I don't know if folks have read, Lindsay and I wrote a blog post about it, we can drop a link in the document. The way we framed that to the NSF was that we would work on having a couple of domain use cases in geosciences, one which would be exactly the kind of geophysical problems that SimPEG focuses on, as well as work in hydrology and work on the analysis of large-scale climate model data. To couple that with the development of infrastructure in the Jupiter and Pangeo ecosystems. For those of you who may not be familiar, just in a couple of words, Pangeo is a project that was originally led by folks from NCAR and Columbia University, to try to basically assemble kind of some of the open source tools like Dask, Xarray, and Jupiter into a coherent environment for cloud-based or HPC-based large-scale analysis of scientific data, where a community could come and basically work where the data is, whether the data is in an HPC facility or the data is in the cloud, bring effectively the compute resources to the data in a way that would be based on open tools. Pangeo has been very successful. It has been growing well. And our grant is kind of a second grant on the Pangeo thread of ideas. And in fact, one of our co-PIs is one of the original Pangeo leads. So I'm here. I may not stay for the entire 2 hours of the meeting, but my intent is sort of in understanding some of the scientific use cases that you folks have in mind, and how we can use that and connect that with this project, since we wrote that as one of the deliverables in the grant would be precisely to use use cases in geophysics to drive some of the development of tools on the Jupiter Pangeo side. So I'm mostly here basically to sort of understand what your questions and constraints and workflow ideas and scientific questions are, to see how we can best basically steer the tech and software part of that development to align with your science needs. So I'm mostly here to basically listen, and Lindsay knows more about this than I do. Actually on both sides at this point. She's actually more connected with the Pangeo team than I am, so I'll be mostly listening in. But I'm happy to answer any questions if anybody has them, and it's a pleasure meeting the new faces. I've heard about all of you folks, the ones I didn't know, so it's great to put faces to the names I've heard about.
Thanks, Fernando. So I guess to kind of kick things off, maybe we can think through, I mean, we've got this document running that's like some of the needs and things like that for development in SimPEG, but maybe it would be helpful to start with kind of use cases and what folks like are most excited about sort of getting involved in, and then we can think about how to start parsing out some of these things. Yeah, I mean, so a couple of you spoke to this. Dev, I might just ask you to mute.
Oh yeah, no problem.
We're just getting a bit of background from you. Thank you. So yeah, so as Fernando mentioned, I guess from my perspective, sort of the Jupiter Meets the Earth project, in terms of data, I've been in touch with, well, Paul Bedrosian, we actually wrote into the grant at USGS. They have some interesting data over some of the Aleutian Islands, and we're really, really struggling to invert it with ModEM. So for Fernando's sake, ModEM is sort of the standard go-to package in MT. And so, yeah, so they were really struggling with that. So like there's gotta be some interesting scientific questions. I mean, so part of what he thinks is the problem is they actually have stations on the ocean floor, and they also, as well as on land. And they can't seem to be successful in inverting all of them simultaneously. So I don't actually have the data yet, haven't actually looked at that, but that's sort of like the data set that I'm interested in eventually working towards. But as first data sets, I know that like Devin's done a lot of work on the synthetic L-shaped model, and there might be a couple other models that we could perhaps think through to use as a bit of a test case.
Yeah, that's actually a pretty good one. We actually have a lot of examples that are already packaged for GIF tools related stuff. So there is the L block, full forward modeling and inversion of the L block. There's also a synthetic TKC example. So you can find that on the GIF tools cookbook. And I acquired real MT and ZTEM data. So I know we're not working on ZTEM right now, but real data from Cloncurry, and did a walkthrough, like an inversion for that. So there's actually a lot of stuff you could compare against the GIF codes.
And Devin, are all of those in the GIF tools, or like are all of the models and the associated data in the GIF tools cookbook, or are they sitting somewhere else?
They would be part of the GIF tools cookbook repository, and you would download a zip file and it would have everything like completed. I think the completed inversion is in there, the true model, every stage it should be available in there.
Yeah. Is that the stuff that you pointed me at, Devin?
Yeah.
Yeah, it's all there. They've got all the data, DM, everything, and yeah, that's what I was using to compare with SimPEG as well.
Yeah, and we even go through looking at the actual data and discussing what coordinate systems we're in. It's very thorough. It's very thorough. So I would look there. I can drop some links if people want.
That would be great. I just, at the bottom of the document, I started an examples list. If you have that link handy, I could just drop it in there. That would be great.
Yeah, I'll fill that in right now.
So I know both John and Joe, you've been doing a bit of a dive into the code. I don't know if you want to just kind of give a bit of perhaps an update of where you think things are at and what your priorities are, and where you perhaps would want support or somebody else to sort of take a piece. Yeah.
Yeah, I'm looking at the code right now, just trying to experiment with how we can optimize it a little bit. I started taking out so that you can calculate the frequencies on the fly, because every time you go to do JVEC or JTVEC, you're going to be going over the frequencies anyways. So you're going over frequencies to calculate all the fields, and then you're going and calculating the JTVEC. So maybe by putting it all together, we'll save some time there. But the option is still available that you can just calculate all the fields at once. So I'm trying to make it so that it can go forward without hopefully coming up too much. And I like,
sorry, the distinction there being that instead of doing like 2 loops over frequency, like one with the forward problem and one with JVEC or JTVEC, we now break it up so we're solving each frequency independently? Is
pretty
that
much.
correct?
That's kind of what I'm trying to, yeah, like solving them all in parallel kind of thing.
Okay.
So you just have to get the frequency or the fields for that certain frequency, and then go through and calculate the rest of JVEC, JTVEC, or yeah.
Okay.
And then I was thinking about trying to introduce X-array instead of having the dictionary passed around. Yeah, just little things like that, and then maybe just even storing the fields to ZAR. Just little things that we tried with the DC. Yeah, right now that's just kind of what I'm playing with, just to see how we can get a little bit faster. Because yeah, I guess what my next need would be was Octree, because I'm trying to speed it up because the tensor is a bit slow. So.
Sorry, go ahead.
Oh, but I was going to say, but yeah, it's maybe something that I can't take on entirely. Like getting all these suggestions from Joe, going like even on the DC stuff, and what I've done to the MT already has been great. So yeah, I definitely wouldn't mind teaming up if that'd be the case.
One thing that we could sketch out, because I think there's potentially a couple different ways we want to parallelize over frequencies. So we could try and do it internally. We could also try and do it at sort of the data misfit level, and just have each like more like the global problem idea. So Fernando, when solving the MT problem, you're potentially doing a sweep over, like we're solving Maxwell's equations at a bunch of different frequencies, and each of those solves is completely independent. So what we could do is have like basically break that up internally and parallelize internally, or we could try to do it at the top level and basically like treat it like a joint inversion. Even though it, well, it doesn't really matter, but each data misfit term could then, like we could break it up at that point because that's basically equivalent. And so I don't know which makes the most sense to do. Does that make sense, John? What I'm?
Yeah, I get where you're going from. Yeah. I guess the thing is you always kind of want to parallelize the most outer, and that would be the misfit, wouldn't it? Over.
Yeah. Joe, I don't know what your thoughts are on that. I know you.
So, I mean, I think I kind of like that approach better, so that we don't have to worry about modifying the MT code too much. Basically, the idea is like you break the survey up into a bunch of different surveys or break it up by sources, right? By source frequency. So each survey, instead of having like 100 frequencies, they'd have like 10 or something. So it's kind of a broader level or higher level parallelism, which is usually better.
And I think what's kind of nice about that is thinking about then like the using a different mesh for each frequency at that point is a little more transparent. Is using a coarser mesh for lower frequencies and a denser mesh for higher frequencies. I mean, we'd need some utilities for that, but the octree is actually really nice for that, is because it's a really natural way to coarsen and refine, which would be pretty cool.
Okay.
It just brings to that we need to get the either need to separate out. I'd like to get the primary secondary approach. I'd like to get that onto the source side instead of being tied into the simulation. Yeah, and then it's that. I think that'd be a lot easier doing that way, and then trying to get the electric field. Like you essentially, yeah. Sorry.
No, don't be sorry. That's a good point. I'm just jotting that down in the document here. Okay.
It'll be easier to apply it to a tree mesh if we separate that out.
Yeah. Okay. One of the other questions, and I think Joe, I would appreciate your thoughts because I know you've been looking at the code quite a bit, is with respect to integrating the natural source forward solve with the frequency domain solve, and having basically, like, what I would like to see, I think, is that we basically don't actually have an MT forward simulation, that all of that is handled by sources and receivers, and we're always just relying on the same forward solve because it is just frequency domain. But that then has the subtlety that we need to, like right now, the frequency domain code assumes that a source has only one source term associated with it, whereas with a natural field, we need both polarizations. So Fernando, we need both polarizations of like the electric and magnetic field to solve the full 3D problem. Whereas in general, if we just have a loop source, there's one source term associated with that. So that assumption is baked into the frequency domain code right now.
So what I've seen in the code is we could make use of a lot of that. That's the only that's the biggest thing, right?
Yeah.
And within the code right now, it's, I mean, I don't know any reason why we couldn't like have it be a combination of like two simulations.
Sorry, two simulations or two
meaning
courses?
That the near surface EM, let's say, would be a combination of, or the natural source stuff would be a combination of the E formulation and the B formulation.
Okay, so in this case, we don't necessarily need two formulations, but what we need is two. So the source, when you actually create the source vector, like the subtlety between the frequency domain and the natural source is that the source, when you call the source, you actually get two vectors back. You get two polarizations. And then when we construct the fields object, we have like two polarizations in there. And then similarly, when we are creating receivers, we need to be able to actually, like the receiver needs to know that a source has two components.
Right. So we had to have specialized receivers for MT and specialized sources for MT. I don't anticipate any problem with that, with combining them. That was something that I went about when we were looking at, or when I was creating the getJ function for simulation. I noted parts where it's like, okay, well, we need to update. We just basically need to update a lot of those implicit functions so that they arbitrarily accept matrices as input as well.
Okay. Yep.
Does that make sense? Like, I think that's all we need to do.
Yeah. Yeah, but that, and then I think the receivers will just take, like the fields object and the receivers will just take a little bit of thought, but I think all of that is wiring.
Yeah, I think it'll be okay.
And then that's kind of cool because then we'll actually have played around with boundary conditions and actually getting boundary conditions implemented in the frequency domain code, which I think opens up, I don't know, potentially some fun things to play with even when it's not natural sources. Cool. I see Dom just jumped in. How was your bike ride?
I went way too far and my back wheel seized up, man. How to get stuck at Main Street.
Oh no.
Sorry about that.
Well, glad you made it. Dom, I don't know if you and Fernando have met.
No, I've seen your talk though at UBC, but no, never probably met. Pleased to meet you.
Very nice meeting you, Dom. And I've heard a lot of good things about you. And so it's a pleasure meeting you at last.
Yeah, it's a small community. It's important for us to talk.
Absolutely.
Cool. So Dom, to bring you up to speed, we're just working, we've got some notes in the document. We sketched out, Devin kindly put some links in for some of the examples that we can look to. And then we were just chatting through like some of the main development items. But actually, if you don't mind, I think it would be helpful for everyone here if you would be willing to just kind of share like what sorts of things you want to get out of this and are interested in working on along the way.
Yeah, I think, I mean, it's not, I don't have much insights of how the MT code works, but I think if we can do the same that we did with DC code, we basically want to be able to scale it up. And industry really wants to have an MT code that can, that can work with industry size things. And the UBC codes are great, I'm sure, but there's so few people who are willing to invest the tens of thousands of dollars to do it. I think they're more willing to pitch money for development in terms of having developers and having it to be open code. So both on the Mira side, both on the consultants and the consortium of companies, they all say the same thing. Go ahead, you basically spend as much like hours as you want to push the code so that we can get our hands on it. So basically that's where I'm at. And I think that document that you started putting together, I think all the ideas are pretty much in there. If we could store sensitivities to disk, that would be probably help a lot to be able to scale up and do a tiled mesh decoupling approach. I mean, all of it is technically there, right? It's just a matter of figuring out efficiency holes in the code. And I think John, you spent already a ton of time on this, so unfortunately, I'm not there yet. I haven't started looking at your code, but it's on my list. What can I say? I'm revisiting DC now, but MT is going to be next. That's it. That's it for me.
Thanks, John. One thing that might actually be helpful for context. So we were just talking about actually how to think through parallelizing the code. And do we actually do it at the internal level, or do we think about it at more like the data misfit level? Could you share sort of like the high level structure of how the global problem works right now?
Yeah, I mean, we haven't implemented it on the simulation class. I have it only for potential fields right now, but basically all I ended up doing is that if we split the problems with mesh decoupling, right? So we're basically just appending blocks of data misfits, and then Dask knows how to basically, when we launch it, we would be launching each blocks of misfit, each batch of data, either on separate machines, or if we only have one machine, it's going to be a shared memory. But I think the MPI style parallelization should happen on the data misfit.
Okay, so it is all at data misfit level.
Well, it's two levels, right? So if we do Dask, then we have a parallelization on the JVEC operations. That could be split on the machines, because that's just a shared memory problem. But then each sub data blocks then can be spun up on different machines. Does that make sense?
Okay, so let me just like explain it back and see if this works.
Yeah.
So the top level, so the JVEC parallelization is actually independent of the global problem, right? That is basically just, we're just constructing a matrix and we happen to be able to do that in parallel.
Yeah, exactly.
The global problem is now we've actually basically broken up our survey and are treating each chunk of the survey as a given data misfit. So it's effectively like a joint inversion of a single survey. Okay.
Exactly it. And so I think the split is natural there. To send those misfit functions to different, if we have like a distributed memory problem, then it would make sense to send it to each, because Paradiso can be done separately on different machines. We don't need to worry about cross-talking because the JVEC, JTVEC requires the Paradiso or any solvers, right? All happens there. So that part makes sense to be on a global memory. Does that make sense still? Am I talking in oblivion here?
That makes sense. Well, and it's nice too, because all you're sending back at that point is just a scalar rather than like
just a vector
information that we're passing. Yeah, a scalar and a vector for the JTVEC.
Exactly.
Yeah.
Basically, the global misfit just gets all the vectors, as you said, just sums up all those vectors, and then we do the gradient step.
Okay.
Regularization happens on the main node. I mean, that's nothing, right? It's just a sparse matrix. Yeah.
So Dom, when you talk about breaking things up, are you still doing the forward modeling on the large scale mesh?
No, the forward is done on their individual meshes, right? So let's say you have either blocks of data or blocks of frequencies. They could all have their own meshes, but then the tile map does do the transpose of like a JVEC on a local mesh back to the global for the gradient stuff. Does that make sense?
Well, that makes a lot of sense for like airborne EM or things like that, where you've got limited footprints.
Yeah.
But for the MT, if you start breaking things up, then you're going to be working with, essentially different boundary conditions on solving that forward problem.
Yes and no, right? Because the meshes should be nested. So in theory, all forward meshes should cover the same extent. And yes, you're going to have numerical precisions that will vary from mesh to mesh. But okay. I think in terms of the connectivity interpolation, they should all see the same global extent.
Okay, that was, maybe I worded the question poorly, but
it's a good question. It really depends how you do your tiling, right? Are you nested or are you like completely decoupling your meshes? Yeah. But right now it's all nested.
Dom, quick question. When you said the MPI style parallelization, what do you mean by that? Do you mean with an actual kind of large amount of inter-node communication, or what did you mean? I mean, MPI can be used in a lot of different ways. So that statement doesn't tell me much.
Okay. Yeah, I'm also not an expert in parallelization, so I'm probably not using the right words to say it. But basically, what I have in mind is that at the misfit level, so basically each local forward problem knows its own mesh. this can be sent on a different node that has its own memory allocation to do its own thing. And then once it's done, it's just sending back a vector like Lindsay said. So whatever protocol we're using to parallelize it, basically we have two levels. We have a level that we can have our local memory usage versus having a global passing of information. Sorry, I don't think I'm making sense there, but can you maybe ask what you mean, what you have in mind?
No, I was just trying to understand, what did you mean by the sentence, the MPI style parallelization? Okay, well, because to me, in my head, like that phrase can mean a lot of things. Yeah, no, I see, but because in my head, MPI is a distributed memory style, but I might be wrong. That's how UBC codes are using it. They're using MPI to split it across nodes, and OpenMP for local parallelization. But I'm sure MPI can be used in many different ways. So I just don't know what I'm talking about.
Like Fernando, I think what Dom mentioned was the difference between the shared memory versus like a distributed memory. So MPI was basically, there's no sharing between the nodes except for the message passing. So I think that's what Dom meant. Yes, thanks, Alec. Exactly.
No, I was trying to understand if there was any more to it in the sense of parts of it being implemented actually where you guys are implementing with MPI a large amount of message passing. Because you can use MPI to do something like Dask, where you're simply managing tasks and your root node just collects, does gathers and collects things, and that's it. Or you can use MPI in the way it's used in most PDE codes, where there's a very large amount of internode communication and potentially with a complicated topology, right? So MPI it may be a better fit for some of those problems than others. The very coarse stuff, something like Dask that only knows how to do that will probably do it a little bit easier, but it can be used in a very broad range of problems. And so I was trying to understand, as you're segmenting, you're breaking down the logic of this parallelization, what you meant by that, that's all. So,
yeah, no, absolutely. And that's something that we're currently don't have any experience, and someone like you and your group would probably help a lot, is we don't really have a good handle on how to do that, to force Dask, to split, basically tell Dask how to split the problem, like do shared memory for that part versus distributed memory for that part. And so I think that's something that with this MT project that we should try to push is to get a good handle on how to do that well.
Right. In a higher level, so basically what we want is, first thing is a matrix vector product. So that's like a very basic level of parallelization that we want to do. And the second level is more almost like an embarrassingly parallel. Like we just want looping over and like a large simulation or even small simulation and relatively fast speed. So I mean those are two key items, and we're trying to minimize the talk in between. So it's almost very close to the embarrassingly parallel problem.
Embarrassingly easy, right?
Well, in theory. In practice, no.
No, it's not easy. Yeah, so that's what I have in mind.
Just to make sure that I understand, so if you're using the tiles for the forward simulation, and you're gonna forward model the data, then you have data organized by different frequencies and a different mesh for each location. And so you talked about using something like Dask, or you talked about parallelization between different nodes and then also between threads on the same node. So I guess I'm wondering what conflicts might happen if you're trying to, it's like parallelizing within parallelizing. Am I kind of on the right track here? So are you planning to partition the work like a different frequency for each node, and let and then on each node you would partition up all the locations, or do you want to partition up a chunk of locations, and for that chunk of locations you would go and solve the problem at all frequencies?
Yeah, so right now it's dead simple, right? Because all the work is done just ahead of time to just break up your problem and say like this chunk of vectors is associated with this simulation, this chunk of vector with that simulation, and then we just delay all those operations for later. And then when we call dask, all it does is just send this to this computer, this to the computer, and that one, and at the end it just stacks it all up and then give you back as just a normal vector. So you don't have to worry about like indexing. You're just delaying your operations.
Yeah, so then if I understand you right, each kind of individual tiny job is a unique solve for a particular location and or I guess mesh and frequency, and it has all of those, and then it just sends them all out and brings them all back.
Yeah, then it's on desk jobs to just like schedule which parts of the vector they want to compute at what time, you know. And,
Okay.
And that's all done for us. We don't need to worry about that part. At least just for if we're gonna for shared memory, we don't have to worry about that part. It's the problem if we're gonna start doing distributed memory, then we need to worry about which jobs we're sending to which pool of processors, that kind of stuff. And
Okay.
that's where we don't have experience right now. Yeah. Does that make sense, though?
Yeah, I think I get it.
Yeah.
I mean, ideally, the dask should also scale up to clusters as well, because there's.
It's in the documentation. You just don't know how to do it. Yeah.
I think our issues come down to we have to figure out a good way to share the solver. Everything else works just like can be just fine. Like it knows how to pass around arrays, it knows how to pass around everything else. It's just the solver is the thing that we're stuck.
But I don't even think so, Joe, because technically, if each block have their own mesh, then they're gonna have their own solver, right? They're gonna solve their own systems internally, and then just send back the vector at the end. They don't even need to share AM. We can split it before that.
Yeah, so that's that's a kind of how we are structuring. So I thought that as an initial shot, we're simply parallelizing just with the frequency. So each frequency have a different mesh. So we're not breaking apart depending upon the location. I mean, that'll be an interesting pathway, I guess.
It's the same problem. It's the exact same thing, right? We're just splitting that vector of data into parts. Either it's spatial or it's frequency. The code doesn't care. We're just splitting it into bits.
Right.
The only bad thing about splitting it up just by frequency is that it limits your scalability very quickly. You can only split it up, so many times. And people aren't using necessarily like hundreds of frequencies for an MT inversion, right?
Right. So it's probably like 10 to 20 frequencies.
Yeah. So that like just splitting up by only frequencies, it's going to severely limit our scalability.
But I mean, that's another, there's another pathway that as I mentioned, just simply parallelizing matrix vector product. You can save so then switching to iterative solver, for instance, you can actually massively parallelize. Because if you think about iterative solver, it's literally just matrix vector product. So if you can parallelize that part of solve of both getting the solution or in the inversion iteration, you can massively parallelize that part, which will speed up a lot.
Did you ever had success, because for a DC problem, man, we tried all the SciPy solvers, and there's nothing that gets even close in terms of speed and accuracy as Paradiso.
I think that the problem that we're solving is still pretty small. If you think about because that's why the Paradiso is so fast. But say it's a problem scale. So let's say for DC problem, you're handling less than 1 million cells. I think using direct solver is pretty fine, and that's pretty fast. But once you move on to, let's say, 10 million and solving a core system like a Maxwell, I think you cannot even use Paradiso. So there's a bit of a split. So if you can it's a choice that we need to make. So let's say the problem that we're dealing with for MP is 10 millions. Then I mean, we cannot even use the direct solver. We must go to the iterative solver. So
it gets smaller. It solves it for each each edge, right?
Right. So
Yeah.
it's not millions. It's not even 10 million. It's more than that, like factor of 3 or 4.
Yeah.
So,
do you think though, Sagi, that scale is actually something that like we need to address right now? Because
no, I don't think so. So so that was sort of the point that I wanted to make. We need to sort of target where we're going and the size of the problem. Then that'll give us a bit of idea. Oh, which solver are we going to choose? Because
there's a lot of work.
There's just so many choices, and we
There's a
probably
lot of work on just
targeted into a certain like size of problem, certain like use cases, and targeted our development in such a way.
Yeah. Doug, what does the UBC codes use? It's all Paradiso?
Mostly, yes.
Yeah. Yeah. I mean, I would be inclined to start with that scale and first, I mean, because I think that's the most commonly used scale for MT is still something that can fit into Paradiso. That seems to me like a reasonable place to start, and then to compare to, I mean, also to just be able to compare with the UBC code with all of these examples that we've already got, knowing that we're using the same solver and that sorts of thing. Like hopefully a benchmark of where things are at.
Well, the version 1, E3DMT version 1, actually allows you to use Paradiso and lets you use an iterative solver.
Okay.
So you could actually run the code with either. Yeah.
Cool. Okay.
So if that's the pathway that we're going, I actually like the Don's idea of breaking apart in terms of locations as well. As long as we're nested, we can set the same boundary condition. What I'm a little bit worried about that coarsening part for EM problem, that interpolation, I'm not sure how accurate it is. So we probably need to test that like a little bit more rigorously, like whether we're getting the right solution, less than our like a error level that we're assuming. So as long as that's kind of okay, I actually really like to break that apart. Even like we can think about, we can break that apart by sounding by sounding. So each MT sounding could even have a single mesh. So in such a way, you can break that up, you can reduce the size of the problem that you're solving a lot. So that's like an ideal, but I'm not sure how well that's gonna work out.
As a first shot through, I mean, I think we like need to think about this a bit step by step, because it would be awesome to be able to try that. But right now we're not even at the place where we can parallelize over frequency. So I think that's where we got to start.
Yeah, exactly.
Yeah,
so
I agree.
But then once we have that machinery in place, as Dom said, it shouldn't be too, I mean, the extension to doing something more sophisticated like that should actually just be at the level of creating utilities rather than in the guts of the code. But the parallelizing over frequencies and sort of getting that is, I think, probably a first key step to unlock some of these next things.
Right.
Yeah, like creating it, basically just a wrapper to create. You give it a full survey, and then it just like splice it into smaller chunks, and then create your global misfit function type of thing. One thing that we'll need to consider, and we should put it in the notes, is that if we start creating a large number of meshes, we should start thinking at not storing the full mesh into the simulation, but only storing like the operators that it needs. Because the tree mesh actually contains it's big, right? And it doesn't compress very well. So if we could store only like the sparse operators, we could save like a huge amount of memory.
And another thing that I haven't played that much with the Dask. The only way that I can get a good scale with Dask, like for a simple embarrassingly parallel problem, was basically storing everything into a hard disk and minimizing the message passing in between. Because I'm thinking about, let's say, like even a vector, let's say we got 1 million cell, where we need to pass 1 million cell size vector from a local to global. I'm not sure, like, I think that'll make it pretty slow, that this Dask operation, which, yeah, I'm not 100% sure. I was actually playing with like a relatively small problem. So that could scale up if you got a larger problem, but
it depends on your SSD. It really depends on how fast your SSD drive is. That's the bottleneck.
Right, but I was thinking about more just within the desk, like if you're passing relatively large size array from local to global, or like a parent to children or something like that. That like I saw a lot of slowdown.
What operation? Sorry, I'm not following you.
So suppose like you do a misfit function, right? So what only thing that you need to pass from local. So you suppose you're doing a JVAC and a local. Then now you need to get the vector. Then you need to pass back that into your global or parent. So like
that should just be a projection, no?
It depends upon how you parallelize. So like a.
Are you talking about the operation of just sending out a vector to all of like, I guess an MPI world, it's like a scatter, or not a scatter.
Yeah, something like that. So I'm not sure like where like exact calculation is happening, but in my sort of imagination, when we're computing the matrix vector product or JVAC or JTVAC, we do that in the local process. And then basically sending that vector back into the global or parent and do the inversion operations there. That's what I was thinking. Maybe I'm wrong.
Well, I think the bulk of time is not spent there. The bulk of time is done in the operation, in the matrix operations, right? Sending a vector, I don't think it's gonna be hurting us. I mean, okay. Like we're spending so much time solving EM and doing all the matrix vector products.
Okay.
I don't know. No, and I'm not saying you're not right. You for sure there's probably a cost to this, but the bulk of time is not spent in.
Right. But what are you passing in between when you're parallelizing?
You mean at the global misfit function side?
Yeah. So what's calculated in your children, and what's send it over to your parent?
The children is sending back a vector full size of the inversion mesh. So that's it. It's a 10 million cell problem. Then you're sending a 10 million vector back.
Right, and then that message passing is not a big deal. Doesn't take that long.
Well, I mean, I'm sure it has a cost, but how much time you're spending doing JVAC? Like you're probably spending 99% of your time doing JVAC, and I don't know. Passing a vector, it can't be that long. I don't know. Maybe you're right, but
no, I'm just curious. Like, what's
when I look at my processors, where they're busy, they're not busy passing stuff over. They're busy doing the matrix vector.
Okay.
Dom, one question following on that. So at least with the things that I've played around with, sort of the vector was never the concern, but passing an object potentially was. So the serialization, deserialization step actually is potentially subtle. Have you run into any of those sorts of problems yet?
Which object are you passing?
So in this case, if you are parallelizing like the global problem, we're then passing a data misfit object, which has the mesh and the simulation, like all of that stuff sort of lopped on. Have you encountered any problems like sending the data misfit objects? So not in the retrieval of results, but in actually the dispersal.
Well, currently everything that I've done was all shared memory. So yeah, that's a good point. That being said, I don't think the misfit object should contain anything more complicated than NumPy vectors.
But it does contain, it contains the simulation, the mesh. So like if you sort of naively serialize that, this is something we should play around with. And I think we might be able to, like, this is where that properties library could come in handy, is figuring out what are the right ways to serialize and deserialize these things. Yeah, because I wouldn't be surprised if we actually try and scale up to a cluster if that causes an unpleasant bottleneck. It probably won't grind us to a halt, but I wouldn't be surprised if that's actually somewhat problematic.
That's a fair point, and that's probably another valid argument to not pass tree meshes around, because they have a lot of back information that they don't necessarily need, right?
So this will be something that you're going to have to spend time on, because it does become the heart in in object-oriented Python codes, this often becomes a pretty tricky point, because if you naively try to serialize container objects, the naive tools will treat them as black boxes, and they will recurse down the object's internal hierarchy, and they will do stupid things that end up being very expensive, because it's hard to be smart about that problem of serializing a complicated object in an opaque way, if you can't make any assumptions, and if the tool doesn't know what it is serializing, it has to take very conservative approaches, and they tend to produce actually enormous costs. So IPython had a kind of a predecessor to Dask, which was the IPython parallel machinery, and we spent years on this. We spent a huge amount of time on machinery for custom serialization. I was just reading through the serialization docs in Dask. These are the docs you folks are going to have to be reading. I'll put them in the chat. So these are the docs that are going to be relevant, because Dask does offer basically machinery for you to say, this is how my objects need to know how to serialize and deserialize themselves intelligently. And one of the critical things is that if you have a container object that is kind of a domain object that represents the physics and the mathematics of what you're trying to do, and it has a bunch of potentially scalar properties here and there, maybe a few tuples and lists, and then a couple of potentially pretty big NumPy arrays scattered everywhere. One of the things you need to be careful to do is, or pandas data frames, which are even worse, is that you never actually retraverse those big objects, right? You need to basically find the data pointers for all those things and make sure that when they get sent, those things get sent in the most efficient way possible, right? So that the actual library that is going to do the communications doesn't take a NumPy array and effectively make a copy of it, which is what will happen naively. And it's very easy to fall into that it basically said, okay, now I'm going to send this array. All right, well, grab it and put it where I'm going to send it. Well, that act could cost you a huge amount of memory, right? And you actually may end up with multiple copies, because then you hand it over to the networking library, and the networking library has network buffers where it will copy things again. So you can easily have 3 or 4 copies of your arrays without noticing. It's extremely easy to fall into that without noticing it. So you will probably profile the living shit out of that, and you will be implementing custom serializers, and that's what the machinery that Dask provides is for, is to give you the hooks for you to say, okay, first of all, I don't need to send this and this and that, because I know I can reconstruct on the other side very easily, or I'm not going to need it for that operation, so I don't need to package it. All of these scalar things, fine, do whatever. And then for these are NumPy arrays, and then I know they're going to be NumPy arrays, and we hand them down to the fast transfer networking code that will do the best it can to effectively tell the actual networking library. For example, in our case, it was in ZeroMQ and C++, you end up saying, okay, you are the one who gets an actual pointer, right, a memory address, and you are told how to walk that memory so that you only copy whatever has to happen at a very low level from a networking perspective, to say, like, copy into the networking buffers, and you give that to the Ethernet card, and like whatever has to happen down there. But you never say, here's a 4 gigabyte array, please make a copy of it to send it, right? And so that Dask has the hooks for that, but there's always a little bit of your own work that has to happen in helping it understand the structure of your objects and to do these things intelligently, because otherwise you do end up, it's a tar pit, right? You just end up wasting a huge amount of time, and potentially it can be anywhere from a nuisance to a catastrophic like bottleneck.
So your suggestion, we should probably start easy, start small with like a few matrices and see how things are passed around. Like how would you tackle like something like this?
Yeah. Go ahead, Anna.
No, go ahead, please.
Oh, I was just going to say the naive approach that I took on NERSC, just to run a bunch of simulations, and this isn't how we want to do it, but it worked well enough. We have all the object serialization for the most part in place through the properties library that just serializes it to JSON, and we can send that to whatever. But I just serialized it to JSON, which is then just a string of stuff that I then passed around. And that was lightweight enough that was good enough to get me going. I mean, we don't necessarily want to have users be doing that, but it was encouraging to see that most of the serialization stuff that we have in place already should facilitate this. And I could see for the tree mesh doing something like, instead of actually serializing, like providing the ability actually to send the function that was used to create the mesh rather than the full mesh. That's not something that we have yet, but that would be a cool thing. Go ahead, Joe.
So what the tree mesh does right now with serializing, which is something so I could get it to work, what it does is that it generates it essentially passes around all the cell centers and the levels of those cells. And essentially the base widths of the cells and the origin of the mesh. So that's the only thing that it sends around when it gets, those are the things that are sending around when it gets serialized and deserialized. So it doesn't send around all the other stuff that it creates on the fly. It just does that. It just does the bare minimum that it needs to reconstruct itself.
And most of them are integers, right? The cell center addresses is just an index, correct?
Yeah, it's just an index. So it's integer.
So all of it can be compressed and sent over pretty easily.
Because Dom, when you were running into issues with the tree mesh, were you like pickling the tree mesh, or what do you remember what approach you were using?
Well, right now I was just storing. I had to hold all those meshes in memory because it's a shared memory problem, right? So it needs to remember all the sub problems and their respective meshes. So the memory buildup is right there.
I see. Okay.
Yeah.
Now, one thing to your advantage is that Dask obviously has, like, you're not going to have to implement the low-level management of NumPy arrays, and Dask has machinery to do that. So it's more a matter of helping it understand the structure of your objects and letting it know where is it going to find NumPy arrays, with which once it sees that, it'll do the right thing, and it's been optimized for that. I see that they have an object, they have a function called register generic, which seems to fit. If your objects fit that pattern, which they probably do, you might actually be able to get away with just help, basically a small amount of help with Dask's tools that just let Dask understand your objects, and that may be enough. Because basically they say if your objects are mostly things that reconstruct without a very complicated custom constructor, and they're mostly simple attributes and NumPy arrays, then if you use this kind of generic thing and tell Dask how to traverse your objects, then it'll do the right thing. So I would do a few tests, and one important thing is you want to benchmark what the actual slowdown on computation is from this. I mean, do you end up basically with your nodes all of a sudden becoming effectively idle because they're just waiting for this stuff to go back and forth? And in terms of basically idle on floating point, right? Because you don't want to be busy either on a lot of network traffic. You also don't want to be busy with CPU, but now it's CPU serialization and deserialization code, right? You don't want to do either of those things, right? So you're gonna want to try to find a good way to understand the impact of both the serialization CPU time and the transfer time against your raw kind of optimal floating point CPU time.
Hey, while we have you, what do you use to profile your Dask operations? I using the console thing, but it's a little bit hard to follow using.
I haven't profiled code in such a long time that I don't know what the current. Way back when cProfile had some hooks that worked well, but this was pre-Dask. I mean, I'm talking years and years ago. I was using cProfile, but I know there's been a lot of work in good profilers lately, so I'm the wrong person to ask actually now. I'm out of date. Lindsay, you might have better ideas of what kind of more recent profiling tools.
I think Joe's probably done more of that recently than I have, but
Just kind of there's line profiling tools that work on Python, but they're difficult to apply to Dask because they essentially measure how long it takes to do each thing. Like each line, okay, it took this long to do this line. But Dask, that's not going to really work in Dask because it's just going to say, oh, it took all the time to do this compute, right?
We want to see what's inside the inside the compute. Yeah.
Dask, I mean, distributed profiling is a spectacular pain in the ass, right? The profiling distributed codes is a spectacular pain in the ass because you basically need profilers running on every node on the compute node, and then you need a way to integrate and aggregate all that data. I actually don't know of any good tools for that.
All right. Well, we'll stick to the Dask to the Dask tree tree thing, but it's not easy.
No.
Speaking of, sorry, go for it.
Go ahead, Dad.
Well, speaking of things that are probably not going to serialize well, we need to talk about fields. Do we want to stick? Do we want to stick to that structure? Because I kind of see why we did it, right? It's kind of nice to be able to just call fields for potential and all that stuff, but it's not the. I don't think it's a simple enough object that we'll be able to easily pass it around. So,
John, I would be curious to hear your thoughts on working with Xarray there. I mean, I had some thoughts a little while back about sort of working with our current structure and improving it and being able to serialize it, but I would be really curious about your take on Xarray so far.
Actually, I haven't got into the Xarray stuff. I didn't get to it last night, but I'm at the step where I'm going to start testing that. But yeah, the fields object is difficult to pass around. That's why I was wondering if we can make it easier, but I haven't dug how deep it goes, like how much of the code we're going to have to fix if we change the field object altogether. I have a feeling that yes, we maybe should, just initially here, but this is what I was going into right now, is just trying to see, like, start off with simple, keeping the fields object and see what we can do by parallelizing that, or then add in the Xarray, as that's what I'm going to do now. Just to see if we get any benefits that way. But yeah, my first impression is we might have to change the object a bit, yeah.
Yeah, no, and I think that's actually totally fair to put on the table, because I think irrespective, we actually need to change the object. There's a few things that are pretty inefficient about how we set it up. There's a lot of reshape operations that happen when we first construct it, which is really expensive when you start to get even moderately large. So the data object, I think we've done a much better job of basically creating a smart dictionary that just knows how to index properly. So rather than reshaping things, you can still call it like you would think to call an array, but all that is doing is then just grabbing the right indices, and so we're not doing any reshaping operations. So I think there's potentially that I think would help, but I think it's totally valid for us to look into Xarray and see if that's the right tool for this. But I don't know at this point. So
I have a really naive question, Lindsay. So when you talk about basically having smart indexing that helps you kind of write natural code and the indexing knows what parts of the array to look into. As you folks are thinking of this restructuring for distributed computing, are you going to have to worry about data locality? Do you imagine that field effectively becoming a distributed object that or effectively subarrays live on different nodes? Because if that's the case, kind of smart indexing approaches may end up with the issue that those indices actually map to multiple places, and then all of a sudden you have kind of cross-node data communication issues that get a little delicate. So I don't know if in this refactoring that you're thinking for parallelization, it does involve effectively cutting up those arrays in ways that will end up potentially across memory spaces.
So in this case, I don't think we'll encounter that, at least at the first pass, because if we parallelize and send each data misfit to each different node, the data misfit is the thing that we're indexing in, so it is actually localized and associated with that given object. And so all of the machinery to orchestrate anything from higher up we would have already needed to deal with that. So I don't think that there's any indexing that we should be doing that thinks it should be grabbing data from there, but actually it should be grabbing data from there. So I'm not concerned about it at this stage.
Okay. Thank you.
So but just kind of the fields object is nice when people want to interact with it, right? It's nice for it being able to have other people interact with it. It's definitely not set up to be accessed quickly or anything like that, right? So just kind of like a broad thinking of the field object, or just kind of like an out there thought, would it be better to move a lot of those operations, like, okay, get E, or like if you want the electric field of something, would it be better to move them into the simulation and away from the field's object, and then just get rid of the whole field's object as a class, and just be, okay, the fields are, it's, it's a numpy array, it's a it's an X array, it's just a thought, like it. Move those convenience operations to the simulation class. If somebody wants to plot the E field, okay, they would say simulation.get E field and pass it the field thing.
Yeah, no, I think that's totally a fair point. I guess I hesitate to do that before we try refactoring the fields object a bit, because I actually think it is a useful construct. It's just right now, because we're so inefficient in the way that we set it up, that it is actually pretty painful. But I'm wondering, if we solve that, if that actually simplifies things enough that it still is a useful construct in the code. And I don't know, maybe it won't be, and maybe then at that point we should totally rethink through where those functions should live. But yeah, at this point I would hesitate to get rid of it before we try and make it more efficient.
That's fine.
It would just be really nice to be able to efficiently ask for the fields, like maybe the electric field along some plane or some surface, just for academic purposes or to demonstrate something.
Right. On top of that, if you think about derivatives, like a field object has a derivatives, and that's actually quite handy to plugging in when you're writing a JVAC and JTVAC. So that conceptual structure is really nice, whereas I
get that. I understand it's a really nice thing to work with right now. I would just, broad thought of something else.
I agree with Joe in a sense.
Yeah, because I agree too, because forming it and storing it right now is super not trivial.
But I think it's truly because we're doing all of these reshape operations. I don't think it's fundamentally something wrong with the idea of the fields object. I think we're not as smart as we could be in how we're setting it up. Yeah.
Yeah, because I guess it's the same problem, right? Either we store it on a simulation or in something called fields. It's just a matter of storing that information well and easily accessible. Yeah.
Right. One potential problem that I thought, because if we're parallelizing each frequency, so we're gonna do even we're doing a simulation, global doesn't really know anything, but it's all the hard part is gonna happen in local. Suppose you compute the fields once, then we're reusing the fields a lot within quite a few other operations like a JVAC and JTVAC. So we probably need to think about how are we going to handle it, because once the loop of the children operation is done, I think we're losing that field. So either we pass that into global or we store somewhere to reuse that, or we can always compute that on the fly. So we need to think about how to manage those things.
Yeah. So while we've got we can keep sort of going on along this line, but I'm wondering if we could maybe pull back and come up with what are the big picture next steps, and what's a constructive, either a constructive example to start from, and then how do we actually practically want to start moving forwards. So in terms of sort of big picture next steps to think through, I think the fields object sounds like something that we should prioritize and see what we can do to improve efficiency there. And so I think first is actually sort of looking at the way that we do the data object and see if those are some easy ideas to transport over. And then with John, if you're willing to sort of play around with Xarray and see like what sorts of improvements we might be able to get if it's appropriate, or if not, I'm not entirely sure one way or another.
Yeah.
Yeah. Okay. And then it sounds like too, with respect to like the idea of the global problem, that's then something we should probably think about trying to get like upstreamed a bit, because Dom, you were saying it's really only implemented for potential fields at the moment.
No, currently it's not on simulation at all. It's
Okay.
only on my research branch, but it's so light on the change of the code for the global problem. Like it's basically changing in the current for loop into a dash delay function, right?
Okay. Yeah.
So it's like very trivial to do. We just need to do it.
Okay, that sounds good. Okay, so that's sort of two low-level things. Then I guess we start to get into some more of the details of the EM side of things. So thinking through, I guess, the natural source EM survey structure, and to see if we can actually then basically get rid of the, get rid of the NSEM forward simulation so that all of the primary secondary is so that all of the primary secondary is handled by the source. And also so that like the basically sort of the assumptions work with two polarizations. Are those sort of the biggest picture things, at least for now, to kind of get us to the next step? I mean, I think some of these things are sort of before we're even getting to the parallelization state, but some of the things that need to be addressed first.
Yeah, I'd like to be able to have like be confident having a really good forward modeling with the boundary conditions implemented, and then having that work on the simulation branch and making a tutorial from it.
Okay.
Because I have a feeling that there's sort of the, you know, how do we solve the problem, and maybe it's not the most efficient way and we don't use parallelization, but for the end user, we've basically gotten to the point where the syntax for running the most basic implementation does not change. So that can be finished. And then once that's in the simulation branch, then we start going in and say, how can we make this more efficient? How can we do this next level stuff? I guess I'm just thinking about potential users and people who are just getting started. And I'd like to be able to have them model stuff and learn quickly, and have a basic implementation, and then be able to go and do some very fancy high-level things once they're more knowledgeable. So
how are we testing the forward right now? Do we have a benchmark, or do we have like an analytical answer for it? What do we do for 3D?
I think the 3D is just testing against 1D and testing sensitivities. John or Joe, do you have any other?
That's all the tests that are doing it now. Yeah.
I haven't done
Yeah.
much tests, yeah.
Okay. So there's two sort of things I'm thinking about with respect to how do we sort of move forward. Is one, what's like an example that we all want to be perhaps working on, and where do we work on that? And then two, within SimPEG, do we want to just like branch off the simulation branch and kind of all start hitting on that, or do like a simulation MT and then we can all kind of branch off of that and play around? I don't know what folks think makes the most sense.
Joe,
What?
you're the captain, man.
I think doing a simulation MT branch for now would be good, and then like, yeah, I like the idea of branching off from that for if individual people want to play around with things.
That's good.
Because then it'll kind of go into this soon. Once simulation gets pulled in, then it's like, okay, well then they've just branched off mass. Like I think that would be the better approach. Yeah.
That sounds good. The only exception I would say to that is perhaps the fields object refactoring and the global problem, because those are basically independent of, I mean, it's the whole code base that's going to be impacted, those, not just MT.
We'll do a simulation, we'll do a fields branch and then a,
yeah. Then with respect to an example, I guess is the L-shaped probably the simplest to start with?
I think so. I think the L shape is probably good because we have forward modeling and inversion examples not only for the octree codes, but we validated those against MTZ3D. So there's a tensor code one.
Excellent.
So then you could use that mesh to and model to validate what you're working on. Yeah. Go ahead, Soggy.
Does it have a topography?
No. We're just keeping it. I mean, it was more just to get people to learn how to use the Fortran code. So I didn't go and see the effects of topography in that.
Do we want to have something that's a little bit more realistic? Because I can come up with something that's like using some, Minecraft stuff to come up with a quick model.
Yeah, I mean, the L's fine. You could just add some kind of undulating topography to that example if you wanted to. Yeah, most of the examples that I found were in real life ended up being fairly flat topography, or the ones that I found with topography I wasn't allowed to use. So
I would vote that we do both, because for sure we want to be able to test against what Devin did with the UBC codes, right? That's the best benchmark that you can do right now.
Yeah.
But yeah, we should definitely test with topography after the fact. So.
Doug, is there a benchmark example you have in mind that's been worked on in the group, even if it's a field data set that we could think?
I mean, the one, the L curve has been our sort of standard. I can't remember what we've done with topography. I mean, we definitely did, but I simply can't remember anymore. I think on a long-term scale, having a couple of problems that we are really interested in solving. So the one that you said from Paul Bedrosian, that actually sounds really appealing, because now we've got some serious boundary conditions to think about, and it's kind of like Iceland, perhaps, but in a smaller scale. And then the other one, which we've talked about for a long time, and I will follow up, is with Daniel in Chile. That was the geothermal example, and that was extreme topography. And so I think that's a nice kind of sort of end examples that you can just kind of keep in mind, and then maybe we can think about test examples that are kind of sort of emulate some aspects of that.
Mm-hmm. That sounds good.
I'll have a tipper data set or like a ZTEM style data set over a ZTEM test survey area down the road if we want to do that. It's not the ZTEM data, but we have the ZTEM results against what we've collected. Yeah, and that's our data, so that's free to, they wouldn't mind.
Excellent. You're muted, Devin. Devin, you're muted.
Sorry. Yeah, we have the L block for all three codes with the ZTEM, and then there's also the TKC has ZTEM involved in it, and then that comprehensive workflow. I have a real data set that I inverted with ZTEM as well.
Okay.
So there's also a lot there for ZTEM when we get to it.
Excellent. Okay, well then maybe I think at least initially just focusing in maybe strictly on the L block, and then we each kind of have our own examples that we're interested in working on, and we can maybe go from there once some of these initial developments are in place.
Yeah, and if we're gonna use pretty significant topography, then I mean, if you've read the manuals for the GIF codes, you have to do a different implementation of the boundary conditions. So we could always start with flat topography, get that working, be happy. Okay, now we have to do a new sort of numerical scheme, and then try and compare that against GIF.
That sounds good. Okay, so if we start with the L-shaped example, where do we all want to work? Like, do we want to start a GitHub repository or Dropbox, or like, what's the easiest way to kind of be able to share notebooks and scripts and things like that, just so we can iterate on ideas? Anyone have preferences there?
GitHub sounds good to me.
Okay. I can maybe just start one in the like SimPEG research GitHub, and then we can just kind of have like a bit of a hopper of a repo, and people can just kind of push and pull. And if you need to even create your own like directory with your name on it, that totally works.
Okay.
Okay.
Yeah, I have a notebook set up for the L-shaped problem already. I could just dump in there if someone wants to go from that.
That would be great.
If the team is okay with this, I would start working on the global problem, but just apply it to the simulation static problem, just because in terms of time, it's more pressing for me, and at the same time, it's an easier problem. We'll be able to probably figure out things a little bit quicker on simpler physics. So that would be my contribution if you guys think it's a good idea.
Yeah, for sure, Dom. I think that would be great. I mean, just having one implementation that we can then sort of make more general that's a great starting point.
That's all I had in mind, yeah.
Cool.
I was wondering if there's some merit to thinking about a document that we could kind of put together, one that would sort of structure some of the, the more practical aspects of what we wanted to do with, with the code, as far as, looking at, things like, finite lengths of wires and I don't know, maybe a whole bunch of other things too, that just, we want to make sure that we can solve, a number of different problems that would arise in practice. And it might also be a place to kind of think about, various geometries or various kinds of geologic structures, that could pose a problem, and just, at least a place to kind of consolidate and jot down ideas that people have about, at the end of the day, I really want this code to be able to do this, or it's got this kind of functionality.
Yeah, well, I mean, for that, I guess a good reference is that MT comprehensive workflow. Like, that was the whole design behind doing that, was being able to address those kinds of issues. Like, oh, I want to use finite length wire for I want to actually define the length of my dipole for electric field measurements. When I discretize, I need to actually have those be on the surface of my discretized topography, because right now they might be hanging out in the air. All that a lot of that stuff is talked about there, but we could make a separate document.
Because I mean, I think to Doug's point, it would be nice to have something, so that's a great reference of perhaps things that we want to be working towards, but something that's a bit more perhaps tailored to SimPEG, and like includes a bit of status information.
Yeah, fair enough.
Doug, do you think and everyone here, do you think that the discourse post that we started would work, or do you want something more like a Google Doc, or what do you think is the easiest?
What about a GitHub project?
Yeah, we could think about that. The thing I've always found challenging is then somebody needs to sort of take ownership of keeping track of that.
Yeah.
I always start with ambitions of doing that, and they quickly wane. But if that's something that you'd be interested in doing, Devin, we could easily create issues and have stuff under there.
Yeah, I think that actually sounds good, because I think I have the time to take that on, and it would keep things really organized. So I'll step up and do that if people are interested in using it.
So is everyone here familiar with actually how that would work?
No, I could use some elaboration.
Sure. So each, what you can do is you can create GitHub issues. So for example, dealing with a finite length of wire in the receivers for natural source EM. We could create that as an issue on the SimPEG repository. And then Devin would file that under sort of the list of to-dos for the natural source EM project. So it's basically like a layer on top of GitHub issues.
Let's see, I can maybe screen share and show Doug a picture.
Sure.
Okay. So I guess everyone sees my screen now?
Yes.
Okay. So you had to make some kind of task for the project under to do. You know, you could add something, and then somebody could decide to assign themselves to this. I need to refamiliarize, but then it goes into in progress, and once you're finished, then you can move these things over to the next one. So you basically would set up some kind of task and what it is, and then a person could be assigned to it, and you would see where they are in the process, and then it would move along to being ready for testing. Somebody could give their comments. If changes need to be made, it goes back, and then finally it would end up in a tutorial section. So the one that I'm showing you right now is a bunch of tasks we had for potential fields. When I was developing tutorials and working a little bit with Dom, I had a list of things that we should be able to simulate: forward simulations, basic inversion, applying iteratively reweighted least squares, and we went through and just ticked off the boxes. So you know, once you can put things in like this and say, yes, we've done this portion of this task. And anyway, I can be in charge of organizing this, and you can get at it through GitHub under projects.
Okay.
So I made one for DCIP stuff and the PFs, and we were doing a utilities refactor, and so maybe I can even go in and see what kind of work has been done on all of these. But I made this to try and organize a lot of the projects we were working on.
So you've got a thing there called documentation. So is that a place where we could look to actually see, you know, for instance, how boundary conditions are being implemented? Or is this just a place where we say, oh, we need to have something written up about?
I think the idea of that project was to update the documentation on the SimPEG website. So things like how is the API documentation auto-generated and stuff like that. So,
but the actual writing of any documentation or keeping track of how a project is proceeding, where is that?
So the actual documentation is.
Oh, go ahead, Lindsay.
Oh, the actual documentation is still on like the docs.simpeg.xyz website. It's a bit, the thing that's a bit unfortunate right now is it's not tracking the simulation work, it's tracking what's on master. And so like what you see up there is not actually currently sort of the state of what is actively being worked on. And that's something that we can try to implement. Is because right now we're deploying the website, or we're deploying the docs through Google App Engine, whereas it would be nice if we switch that over to GitHub Pages, which Bain did for us for the discretized docs. And I think that makes it a bit easier to have basically multiple versions of the documentation, so that you can look at what is master versus what is simulation. Right now, nobody actually sees what the simulation docs are, which is unfortunate. So that's actually potentially a to-do, is to look into getting the docs up onto GitHub Pages.
Yeah. But even for your idea, Doug, right? If you have a wish list of things you would like the NT code to accomplish, we could create a tab, a wish list, and then you put all your ideas in there, and then we slowly chip away at it, you know, move it to like a progress when someone wants to take it on. But at least it would be logged somewhere. It's better. I think it would be better to put it in this format than just a Google Doc, because Google Doc will just kind of lose it. It needs to be logged somewhere. I would think.
Yeah, and you can link it to issues, which is nice too. So you can say, okay, this task has been, we've made an issue, and then when that issue is closed, then the task ends up being completed. Like, it's a way of combining all the good things about the Google Doc with good things about keeping track of stuff on GitHub, and then just a visual set of tiles to say where everything is.
Okay. I'm unfamiliar, but I like it. So yeah, let's try to do something like that.
Yeah, and I mean, you're the boss, so you can just harass any of us and say, I want to see it now, and we'll hook you up. So
that sounds like a great idea. Okay, Devin.
Yeah, he's your boss, man. It's gonna be you.
Okay. Excellent. So, okay, on the immediate action items is I'll get a GitHub repository going, add everyone here under the SimPEG research that we can just use as a playground for the MT. And then we can start to write up some of these tasks perhaps as issues, and then figure out from there sort of who is interested in taking what, who's best suited to take what. And yeah, start to figure out a bit of an order of operations. Yeah, how does that sound?
sure. So then I'll make this project in the, do we want it in the SimPEG repository, or do we want it in this projects repository that you're just about to create?
So I think for this one, let's start with one in the SimPEG repository, because most of the tasks are going to be development tasks on SimPEG. And then if we need to organize stuff around the examples, we can then start to think about one for the examples repository. But at least for the stuff that's basically we need to go in and tinker with SimPEG code, then we can keep that in the SimPEG repository.
Yeah, I agree.
Excellent. Okay.
So, just another thought about all the branches and stuff. Maybe I think it'd be a better idea to play around, to use this time for you guys to understand how to fork to your own repository and work from there. If we're all playing around with MT codes, fork it to your own repository. So we'll make a simulation MT branch, then you can fork that branch to your own repository and play around with it.
One hesitation I guess I have with forks is it is a little less fluid to be sort of sharing and asking somebody to sort of jump on and iterate exactly off of what you've done. A fork is much more so as an individual developer, you go and do your thing and then come back.
Right. That's why if we're all playing around with these things individually, it might be a better avenue for that.
Yeah, I mean, so individually, totally. But I guess with some of these things, I could really easily envision hey, Joe, could you just check out my branch and see what we are working on here? And then you and I just work together on a branch. I mean, at least in my experience, that's been way easier on branches than on forks. But yeah, I don't know if anybody else has. I mean, I think it's totally fair if we're going to just go off and sort of play around, but if we want to sort of be working together, I personally would prefer to be on branches.
It's really up to you guys, mostly Joe. I mean, since you're the manager of all this, to me it makes no difference to fork. It's really yeah, I can fork.
Just don't create pull requests arbitrarily. How about that?
Sounds good.
Yeah, I can do that.
I can do that.
Because the pull requests, like I said, they trigger things to get built twice if it's from. Yeah, if you really wanted to have a pull request going to chat about it, I would say it would be better to fork it to your own branch and then pull it from there. That way, it doesn't get run twice. But just don't do arbitrary pull requests just to chat about things. There's other ways to do that.
Okay. Yes, boss. I'll ask your permission before I PR.
I think I stole the simulation MT branch already. So
Yeah, that's actually maybe one thing we can take a SimPEG meeting and do a branch tidy up. All sit together and delete branches. It'd be great. Perfect. Okay. Are there any other questions, thoughts?
I got maybe one more thing. I was gonna pick Dom's brain about pseudo 3D inversion with MT. I think you guys are much more advanced in terms of the octree and the 3D modeling, but I think there's some value in having the 1D modeling in there. So I was gonna do that, and I thought we could maybe do a pseudo 3D inversion. I think Joe's right about the recursive solution. It's much faster, much more stable. So I'm going to implement that as my 1D scheme.
I think we should have a separate meeting with SUG, because we were talking about bringing the Stitch 1D to the main SimPEG, right? SimPEG EM1D to the main SimPEG, and that's going to be the same implementation, right? We basically need that regularization and all that stuff. So I would just say let's do another meeting just about Stitch GM.
Yeah, I think the thing I wanted to know was, I mean, basically in the Ford simulation, only cells or areas under different receivers are going to produce data. So basically, the sensitivity of a lot of cells in the 3D mesh is actually 0 if you just were to think about it. So it's kind of like the number of parameters that directly impact the data are different than the number of model parameters that we are applying a regularization to.
Yeah, I mean, we can go over it another time, but basically the idea is that the 3D mesh doesn't exist. It only exists if you want to see it in 3D. Otherwise, it's a Delaunay. It's just a Delaunay regularization. So you're not seeing a 3D mesh, basically. But we can go over it later. Yeah, don't worry about this stuff. Once you're really happy with the 1D inversions, after this it's just mechanics that we already have for the airborne.
Yeah, I mean, I figured any kind of interpolation and regularization, you already had it, but I guess it's not added to SimPEG yet.
Well, Suggy has it. We'll bring it over.
Okay, cool.
On the field side, Dom, are you imagining actually storing fields on a hard drive using a ZAR? Is that where you're going?
I was going to try that.
I was okay. So my feeling is that we probably just want to not store fields. Just basically only store AM, do the operation, and then after this, and then copy on the fly. Yeah. But I think you have a fair point. If we do distributed memories, and you're not storing the sensitivities, then you have the problem of having to carry on fields around. So I'm not sure.
I would say having fields on disk if you're doing like JVEC and JTVEC implicit, like without forming J, it'd be a nice idea to have the fields on the disk if they're really large.
Right. So Fernando, actually, I have a question for you. So I'm thinking about scaling up. So let's say we have thousands of nodes, and each node want to access to something in the hard drive, like a ZAR file. Do you think that's actually possible to? So I'm not even sure. Where are we going to store? So in our cluster, we have a temporary hard drive that all the machine can access to that temporary hard drive. So I'm storing that all of those big arrays as a ZAR into those temporary hard drive.
So ideally, each of those things would be stored on the local machines. So if you're looking at your HPC clusters, there's details on how if you want to write to the local machine, you can do just that. And those kinds of things should be written to the local machines. That way you don't have to deal with all the network communication of syncing up a bunch of files and pulling them over network. You don't want to do that.
Okay, I see. I see. So we can break that apart and then like store in a local machine. Is that I see.
And this is where it's like the break happens on the misfit, right? Because if we break it on a misfit, then each misfit has its own field object, which can be stored locally. Yeah, makes sense.
Yeah, that sounds actually good. So Joe, like we can instruct, oh, where are we going to, like I see, like what machine and where we can store like those local files.
So there should be ways, like the HPC people should have a good understanding of how to store things locally and like what drives to access and where to write things to. Because it's dependent on the machines and things.
Most kind of well set up clusters, HPC environments will have a regular naming pattern so that you can say, if I write to /local/data, whatever, that path, whatever machine I'm on, that path will resolve within node. That path never can resolve across, and it's never going to be an NFS mount. It's never going to be something that involves network cross-mounting. And that's the job of a good kind of cluster HPC admin, is to configure things so that you have easy ways of uniformly distinguishing between what is shared storage that all the nodes can see, but that typically is expensive to access, especially if you access it simultaneously, because you create these nasty storms on the network backplane that clog everything up, versus paths that resolve guaranteed locally, guaranteed no network traffic. Often they're going to be either SSDs or even RAM disks if you're really getting fancy, or Optane or something super expensive, but they're going to be very, very fast to access. And you can know for sure that if you write to that path, so you configure your codes to always write these quantities go to these paths, and wherever machine it is, however the jobs end up distributed, it's always guaranteed to be local. So now the catch is you need to find out that information. That's not something you can encode in SimPEG. That's something that is always going to be site-specific, specific to however your cluster and machines are configured. So you can need to look it up. The only thing you need is SimPEG to have kind of enough flexibility, basically, to say if I know how to express those data patterns between global data and local data and whatnot, I can tell SimPEG that thing once, and then it'll do the right thing. But you're not going to be able to encode that knowledge directly into SimPEG.
Like basically just a string. Could we just could we just have a string where to store a ZAR, and just pass it to the object and say you're going to store your ZAR to this, to this address?
At the end of the day, they're paths. Now that's a much more complicated conversation that can't happen in 4 minutes, and I don't want to pretend to know what you folks are doing on that, but it's the big, in a sense, it's the big debate that I think is actually happening, and that in a sense, the Jupiter Meets the Earth project with its kind of Pangeo family does bring that debate to the surface, but I don't know where SimPEG is, which is sort of the debate between path level access to data and effectively object store level access. And I think right now, a lot of scientific communities are effectively undergoing a bit of whether it's a transition or a rethinking, however you want to call it, because when you start working with large scale data in the cloud, you actually don't want to be thinking in terms of paths, of file system paths, right? You need to be thinking in terms of basically the kinds of storage primitives that cloud systems offer, which are typically object stores with bucket addresses that are these generic things that don't exactly look like a file system path, right? The HPC world, on the other hand, comes from a tradition that is kind of a continuous outgrowth from like desktops and clusters and then HPC machines, which is very, very explicit path-oriented. And those two philosophies collide a little bit. And it's a little bit of a question, how do you want to architect a code? Do you want to architect a code to allow the user to have very explicit file management, which feels very natural and very comfortable and very familiar because it's what everybody's used to, and it works all the way down. It works from the laptop to the supercomputer. But when you start accessing remote arbitrary data that is behind a cloud object store system and whatnot, that model doesn't work as well anymore. And there's some advantages to that, because then all of a sudden, if you make that if you kind of accept that you have to cross into that other mode of data management, then all of a sudden global data is okay. Data that might actually be stored in different data centers can resolve naturally. That's what the DAS Gateway project is about. It's about a way of basically giving you remote DAS workers that can live co-located with your data on any data center on the planet across Amazon regions, right? And so, but it's a different way of thinking, right? It's a different way of structuring your codes and whatnot. And I'm not going to pretend to tell the SimPEG team what to do on that. I don't even know exactly where you folks are in the thinking of that.
Yeah,
process.
we're not there. We're not there.
So yeah, I don't want to kind of overstep my boundaries here. I'm mostly here to learn. So
I learned a ton by your 5 minute explanation here. That's great. Thanks for that. Yeah.
I need to step out in a second, so I'll just say my thank you to all of you, to Lindsay for inviting me. I greatly appreciate your invitation, and to all of you for being welcoming and patient with my questions. And I hope whatever I said was somewhat marginally useful. But it's a pleasure meeting you all, and I hope through this project that involves Lindsay and Jupiter, we'll continue connecting.
Thanks, Fernando.
Likewise.
Yeah.
Thank you. Bye. I should probably get going too, guys, unless you have a final remark.
No, I mean, just if there's anything anyone else has to add before we wrap up. I guess one like quick housekeeping thing. I was thinking for communication, just on like the EM Slack channel on this. Does that make sense? Yeah. Okay. Perfect. Doug, you looked like you were about to say something, but you were muted. Oh, okay. You're still muted, by the way. Perfect. Okay. Thanks, everyone. I think this has been pretty productive. I'll get some GitHub repos going, and then we can, yeah, make some next steps from there.
And
Go for it.
I was going to say, I'm going to start to take some of the items in the Google Doc that we have going on and make tasks for a project and share that.
And there's an interesting talk at 4:30. This is going to be the first BCGS online symposium. Joel Jensen's gonna destroy inversion. He's gonna give the big caveat of inversion. So log in if you wanna see the talk. 4:30.
Can you drop?
Yeah.
I'll drop the link. Yeah.
Thanks.
All right. See you in a bit.
Yeah.
Do you have the link for that?
Yeah, I'll put it on. I'll drop it on site.
Okay. Thanks, Lynn. Bye, guys.
All right.
Bye-bye.
EM branch.
Thanks, everyone.
All right. Bye-bye.
Bye.
Hi, guys.
See you, Joe.